Hello everybody, this is me Khalid Mehraj Malik over again with you people with the second video. And the very first video that we have discussed, the lecture that we have discussed for the very first time yesterday, it was for the basic networks, and in which we discussed network analysis and the parameters like what is a tree, what is an incidence matrix, and so on. So in today's lecture we shall be discussing certain theorems like Thevenin's theorem, Norton's theorem, Millman's theorem, Talligen's theorem, etc. So why are those theorems to be studied in electrical? They are basically to reduce the complex circuits into simpler ones and thus making the work easier for us for the sake of calculation. Okay, starting off with Thevenin's theorem today. Thevenin's theorem. Friends, what does this Thevenin's theorem do? This reduces our complex given circuits that are given as problems for us, as questions for us. This theorem reduces those complex circuits into simpler ones and thus makes the work, the making out of that very problem very easy for us. Okay, let us draw a circuit. Okay, so here we have a voltage source. Let us name it VTH or VT simply. You can write as per your desire. This is the Thevenin's voltage source. This is the internal resistance that the Thevenin voltage source has. We write it RT, HR simply RT. Okay, let us wipe out the subscript TH. We shall write only RT, VT, sorry. So this is load resistance. The resistance that we have applied to this very circuit as a load. Something, anything can be a load, that is the power absorber. This is the power transmitter and this part is the power absorber, and it utilizes the electrical energy basically. And here we have a current, that is I, or Thevenin's current IT. So what is the formula? Here we can do like this: I equal to VT upon RT plus RL. One resistance is the internal resistance of Thevenin's voltage source, and another is the load resistance. Here we can find I like this. So this is an ideal circuit of Thevenin's theorem. But as all of you know, every circuit is not as simple as this given circuit that we often see in our question problems. Every circuit is not as simple as this. So how we are going to solve those circuits using this theorem? Let us see. Versus this Vs. This is the simpler one. Let me make, for citing a question, exemplary question, let me make another diagram that will be more complicated than this, and then we shall reduce it into the simpler form. Okay, here let us make a voltage source. For example, say it is 6 volt. Okay friends, so another resistance we make here, still another resistance. Here we give a dependent current source. Let the circuit be like this. This circuit can be further beyond this portion, but we have been asked to find the Thevenin resistance, Thevenin voltage or whatsoever parameters up to this point only. So let us name those 2 points as A and B. This current source can be written in the form of a voltage divided by some parameter like resistance. So say this current source has value VAB divided by 2. Okay, so suppose this is 4 ohms resistance, this is 6 ohms resistance. So what we are going to do here, we have to make all those parameters. We have to get what is VT, then we have to get what is RT, and then we have to get what is, RL will be given anything in between those A and B points. In that simpler way, we will be able to construct this very thing into this form. Okay, so let us perform the step 1. Step 1. We have to find voltage VT. Find voltage VT, Thevenin voltage. For that purpose, what we shall be doing, we shall be short circuit the middle leg, short circuit the middle leg, that is the current source. Okay, when we short circuit this current source, this thing is wiped out, this very thing is wiped out, it will become something like this. This central current source will be wiped out. What will be the effect of this? The effect of this will be that the voltage between those 2 points, the potential difference between those 2 points A and B, that will directly come up to here. It will form VAB between this point, VA and VB. Okay, so let us apply KVL. Applying KVL, what will happen? We have to find VT or VAB. That VT, we have to find VT, Thevenin's voltage, that will be VAB, the difference between potential of this point and potential of this point, that is VAB. VT or VAB will be equal to this current source multiplied by resistance. Though it is in the it looks like it is some voltage, but it is not voltage. It is voltage divided by some parameter like resistance. So it is a current. Basically, it looks like it is a voltage, but it is a current. Okay, multiplying a current with a resistance, it gives VAB upon 2 multiplied by 4, then plus 6 volt, because this becomes I into R becomes V. Current into resistance becomes voltage. Voltage plus this voltage 6 volt. In this way, we get VAB is equal to 2VAB plus 6. So VAB is equal to minus 6 volt, or Thevenin's voltage is equal to minus 6 volt. So this is the step 1, which is complete at this point. What we have to find next? This thing has been done. The next thing that we have to find is RT and this current I. Okay, so in order to find this current I, we shall perform step second. Okay, so we shall be doing like this, short circuiting this point, short circuiting this very those two terminals. We shall short circuit those two terminals. Okay, we shall be doing like this. And then we shall be open circuiting at the same time simultaneously this current source, and we shall only keep a voltage source here so that we may get the current 6 volt. What was the value of this resistance? It was 4 ohm. What was this one? It was 6 ohm. So to find what will be this one, we have short circuited this one, and this will be a short circuit current. Sorry for the inconvenience, it was to be short circuited. This will form a short circuit current or Thevenin's current. So what will be the short circuit current? This short circuit current will be what is current? V equal to IR, then I is equal to V upon R, 6 volt upon 4 ohm ISC, or simply I, that is I R I, that will be what is it? I think it is 1.5 ampere. Okay, so this thing has also been found. What we have to find now? We have to find Thevenin's resistance. So Thevenin's resistance will be found by dividing Vt divided by ISC, short circuit. Why short circuit? Because we have short circuited this current source, and the current that has gone through this resistance becomes absurd. There is no current flowing through this I equal to 0 because it has short circuited and completed the path from here. Okay, so what it will be, RT will be equal to, what was our VT? VT was minus 6 volt. Minus 6 volt upon, what is short circuit current? 1.5 ampere. So we shall be getting the value like RT, Thevenin's resistance, is equal to almost minus 4 ohm. So all the three things have been found out. So we shall make the same circuit like this. We shall write Vt equal to minus 6 here, RT 4 ohm, and I 1.5 ampere. So this circuit will be reduced into that form. We shall write values against those things. Okay. So in this very simple way, Thevenin's any numerical problem that we are given to us that will be reduced into Thevenin's simple circuit by the two steps that we performed here and putting into this formula. Okay, you people may note it. Then we shall wipe it out and go to the Norton's theorem. So we are done with Thevenin's theorem now. So we shall be working out Norton's theorem now. This theorem is just similar to the Thevenin's theorem, provided that it uses a current source and does the methodology of reducing a very complicated circuit into a simple circuit as against to that of a Thevenin's circuit. Okay, so let us make a constant current source here. Here we have a resistance in parallel, and then we shall have a load resistance. This will be called a constant current source. We shall also, since there is no element here, this is short circuited branch, so we shall write it ISC, short circuit current, or Norton current. Okay, this will be Norton resistance, and this will be the load resistance. So what will be the current through load resistance? Here a current IL will flow through the load resistance, and a current IN, Norton current, will flow through this Norton resistance. Those are the two different things, Norton resistance and load resistance. Those are the two different things. So IL will be equal to IN into Rn upon Rn plus RL. This will be the formula to find IL. So the question here arises that every circuit that we are given will not be in the form of this very basic Norton's circuit. So how we shall be reducing that into this circuit and then finding those parameters? So we shall do a numerical problem over this. Okay, just a simple diagram we shall make like this. For example, we are given a voltage source here. It be 20 volt. Here be another resistance, another resistance, another resistance, and then we have a load resistance here. Let the values be 4 ohm, 5 ohm, 6 ohm, and 7 ohm sequentially. Okay, so does this circuit look like this basic Norton circuit? No. How we shall be reducing it into that very thing? How we shall be converting? The main problem here arises how we shall be converting this voltage source into that current source of Norton. Moreover, there is no resistance here in the basic Norton circuit, and here we have a big problem. We have a resistance here in this branch also. So how we shall be reducing it into that? See, it also has two steps. Step first, to find Rn. if we have to find Rn, what we have to do? We have to short circuit this voltage source. Short circuit. Sorry, we have to open circuit the voltage source. By open circuiting this voltage source, what will be the net effect? It will be something like this. Something like this. But considering that this middle branch corresponds to Norton resistance, we shall not be writing this. We shall instead be finding the true value in response to this. We shall be considering this is the false value. We shall be trying to find the true value. So, keeping a view from this point, what we see if we short circuit this on short circuiting the resistance corresponding to Norton resistance. This implies what it will be. It will be something like this. What was the value? 4 ohm, 5 ohm and 7 ohm. So what we get from here, Norton resistance Rn will be equal to 5 ohm and 7 ohm are in series. 5 plus 7 parallel to 4. Norton resistance will be 12 parallel to 4, making the reciprocals of those resistances, and then calculating out the parallel resistance is a cumbersome work, and we shall be using a shortcut trick here, bigger upon ratio plus 1. Which one is the bigger of those two resistances? 12. 12 upon, what is the ratio between 12 and 4? The ratio is 3. 4 3s are 12. 3 bigger upon ratio plus 1. Ratio plus 1. 12 upon 4. Rn equals to 3 ohm. So here, this Rn has been found out. How we shall find In? How we shall find In? That is a cause. Now, we shall be finding Rn by another method, in which we shall be doing like short circuiting this resistance, and considering this loop. Step second, short circuit the resistance corresponding as false to Norton resistance. So which is the false replacement of the original Norton resistance? 6 ohm. So we shall be short circuiting it. It will be the ISC. What is ISC? ISC is IN. So ISC will be, no current will go in this branch. I equal to 0. Since the current will follow its path like this, because this has been short circuited, there will be no requirement for those resistances. So IN will be ISC, short circuit current will be 20 volt upon, since only this resistance is applicable for us now, those resistances are absurd resistances because it has been short circuited. 20 volt upon 4 ohm, short circuit current is 5 ampere, or Norton current 5 ampere. 7. This parameter has also been found. All the three parameters have been found, and in this very way, if we are given with this load resistance also, then we will be able to find IL, the load current, the current that flows through our load, are the points that we are given, up to which we have to find Norton's equivalent circuit. Okay, thank you. So with this we are done with our Thevenin's theorem and Norton's theorem today. I was planning to go up to the Thevenin's theorem and Millman's theorem, etc., superposition theorem, but due to the time constant, so that the video also will be up to the par, up to the apple pie order, so stopping here today, and in the next lecture we shall be discussing further theorems that we are to study in this very section. Okay, thank you.